the Grothendieck-Katz curvature conjecture. I'm going to come back to it today to give the generalization, and because of Nick's previous lecture introducing the character variety of a Riemann surface, the variety of representations of the topological fundamental group, I will reverse the order and introduce Simpson theory and the conjecture we are after. So we don't take a Riemann surface, we take more generally any smooth variety over the complex numbers. And then we look at, we have Simpson constructed, so let me assume for simplicity that they are projective. So if they are not, there is a generalization, but we won't talk on this. And then Simpson introduced 3 moduli spaces. I mean, he didn't introduce, they were already partly pre-existing, partly not. So Simpson. So we have 3 moduli spaces. The first one is the one Nick introduced, and which he denotes slightly differently. So this is, people call it the character variety. And that's the moduli space of representations of pi1 modulo conjugacy, pi1 being the topological fundamental group, and this is usually denoted by MB, and B stands for Betty of X. And then, of course, we can put a rank here. R will be the rank. And then if we look, so this is a complex algebraic variety. And its complex points is precisely the set of representation of the topological fundamental group of X, so based somewhere, in GLRC, and then modulo conjugacy. So I don't really make it very precise, and for our purpose, we can get rid of many difficulties of this construction here by just assuming that we are looking at irreducible. So irreducible representations. If you like, those are the stable points of this moduli. So this is one moduli, and the second moduli here is the so-called Durham moduli. So I forgot to write here, no I did, B stands for Betty, and DR stands for Durham. And the Durham moduli again on X. And again, when we fix a rank here, so that's the same rank as before, except that one cannot read it. And then when we look at the complex points of this, those would be precisely the inabla we introduced yesterday, which are integrable connections. And because X was assumed to be projective, whether I take them analytic or algebraic is the same by Gaga's theory, so this is algebraic integrable connections. And then to refer here to irreducible, we have to say here irreducible as well. In the category of connections, and those are the points here. And we should say here isoclasses of inabla. And here the isoclassis, this is hidden in the fact that we look modulo conjugacy here. And by the Riemann-Hilbert correspondence we had before, so RH, then we know, we can derive from this that analytically, so complex analytically, those two moduli spaces are isomorphic. So complex analytically. And there is a third moduli which plays a tremendous role, and in fact which show up in a hidden way in Nick's lecture an hour ago. This is a moduli of Higgs bundles. So let me write here, and let me use the notation of Carlos Simpson here. And he doesn't say Higgs, he says Dolbeault. So DOL stands for Dolbeault. So again, on X, and we fix an R, and we look at the complex point of this, and those will be something, the points here are easier than connections in the sense that this is basically the same definition as a connection, except that the homomorphism from E to omega 1 tensor E now is really linear. So those are the so-called, let me write V comma theta, where theta now is a linear, all linear, homomorphism from V to omega 1 x tensor V, and there is this integrability condition which we had in nabla here, but here it's much easier to understand the sign rule, so I don't write it. So, which has the property that nabla, wedge nabla is 0, that means we can build a complex out of it. And now I have to refer to the stability condition here, irreducible, and now irreducible, this is phrased in saying that this is stable in the sense of Mumford, and I don't want to insist too much here. So stable, I have to fix, so this means slope stable, so either, well, I should say here, chi stable. Just take it as a blackboard here. So this is chi stability. I don't want to introduce this because it will play not much of a role in our discussion here. You can say that if I take any sub-object, let me just say in a loose way, if I take any sub-object, so the sub-object means it's stabilized theta, and then here I forgot to say that the Chern classes of V are 0. So this is hidden in the chi here. So we want that theta stabilizes a sub-object and the Chern classes are 0. So we have this Chern classes here, and here this is saying that if you like, let me just write the degree on curves. This is not correct here. Of W have to be strictly less than 0. So I apologize for this. I don't want to enter into the details here, but there is a condition which is called chi stability, which corresponds to irreducibility on this side. And then the big theorem is that this Dolbeault here now is real analytically isomorphic to the moduli here. So for example, before I proceed here, let me tell you what it is for rank 1. And let me assume for simplicity that X is a curve. So it's a projective curve, even though it's not necessary, but that enables me to kill the torsion. Then, what is the first space here? It was already on the board this morning. Then this is just, well, R is 1, so that's the rank 1 representation here. So we are in GL1 of C. This is C star modulo conjugacy. But because it's commutative, conjugacy does nothing. So we are just looking at homomorphism from pi 1 to C star. So I'm looking at the complex points here. But now pi 1 had been described explicitly by Nick this morning, but at any rate, even if there was no explicit description here, this is just H1 of C star. Okay? Now, the RAM moduli, or let us do the Betty moduli, it's easier, the Dolbeault moduli. Then this is rank 1 Higgs bundle. So what are rank 1 Higgs bundles? This is a line bundle which has Chern class 0 together with the homomorphism from the line bundle to itself tensor omega 1. But if V has rank 1, and because this homomorphism is linear, I can cancel V on both sides. And that becomes just a differential form. A global differential form. So the Betty moduli is a Dolbeault moduli, I'll apologize. In this case, this is peak 0 of, let's say, of the curve, cross H0 curve omega 1. And now the RAM moduli, what is that? Those are the connections on rank 1 line bundles. So I have a forgetful homomorphism from the RAM, so let's say of rank 1 here. I can certainly map to peak 0 by mapping, I'm just looking at the complex points here. So we have here E nabla, but E has rank 1. And then because it has a connection, it has Chern class 0, so it lands here. So I have E. So the class of E. And then this, in fact, it's a group. In fact, it's even an algebraic group, but let us forget this for a moment. And then when we look at the fibers here, that means we are looking at connections, the underlying vector bundle of which is trivial. But this is just a global differential form, which is closed, and then Hodge theory is telling us that any global differential form is closed, because we are in characteristic 0. So in fact, it's a fibration here. So I just write the fibers here. This is H0 C omega 1. So now it becomes an affine bundle on peak 0, and in fact, this affine bundle is not trivial. So you see you have three very different algebraic structures. One is just this one. So this one, algebraically, this is just GM to the power of the dimension here. This one is peak 0, in particular it's affine. This one has a projective piece and an affine piece, and this, but this is trivialized, it splits, and here it's a fibration with the same pieces here, but it's not split. So this is a picture for rank 1, but in higher rank, so now comes the definition. So for R at least 2, and this is where we don't understand anything, because that reaches the property of the fundamental group, the non-abelian property of the fundamental group. So for R equals 2, then those moduli spaces, those are all analytically isomorphic over R because of the theorem of Simpson here. And they have several components because there are algebraic varieties. I said there are algebraic varieties of finite type, so there are finitely many components. And then it just so happens sometimes they have in particular zero-dimensional components, or if you like, isolated points. So we remark here that because of this fundamental theorem of Simpson, the isolated points on those moduli, we have, because they are all isomorphic as even topological spaces, the isolated points, they are all, those isomorphic takes isolated points to isolated points. And consequently, they become a new word we call rigid objects. So rigid objects, they become a new terminology. Rigid objects are isolated points of either M Betty or M Durham or M Dolbeau. Because the Simpson correspondence is taking them, we can think them as representation, so it's a rigid representation, and it means we cannot move it because in the moduli it's an isolated point. But then the theorem telling us that all those moduli are isomorphic is telling us that if we think of this representation via the Riemann-Hilbert correspondence as a connection, but the connection we cannot deform it. And if we think of this connection as a Higgs bundle via the Durham-Higgs correspondence of Simpsons, then we cannot deform the Higgs bundle. It's not trivial because the fact that we cannot deform topologically, we can believe that once we know I mean, for example, if you think of the classical Riemann-Hilbert correspondence of the 19th century, if we cannot, we say we cannot deform algebraically the representation of the fundamental group, then maybe we could deform it analytically, and then we would have a deformation of the Durham side. But this is not the case. That's the strength of the theorem here. And now comes, and now I relate to yesterday's lecture, the conjecture of Simpson, which is an extremely deep conjecture. Again, so conjecture. The conjecture of Simpson tells us that those rigid objects, and I just say objects because I can't say again representation or connection or Higgs here. So rigid objects are of geometric origin. So you see, this is very profound, because you take an isolated point of those moduli, you really don't know where it comes from, and he tells you there is a variety. So this means I recall the definition we had yesterday on the board, and in fact the board works much better than yesterday. Maybe the chalk works better. Yes. So I apologize for yesterday. So i.e., it means that there is y to x, which is a projective smooth, y to u in x, so there is a u here, which is open and non-empty. Of course, when I say open, means Zariski open. We are doing algebraic geometry. And projective smooth morphism such that viewed as a connection, inabla is a subquotient of a Gauss-Manin connection. So that means Rn F lower star of the relative Durham complex together with the Gauss-Manin connection here, and here there is an N. So where does that come from? It's very mysterious. Okay, so that's conjecture, and again you see, yesterday we were introducing, we were saying connection, I give you first a finite connection and then connection with finite monodromy, and then more generally connection of geometric origin. And then Simpson is telling you, among those connections of geometric origin, there are those which are coming from rigid points here on isolated points on the moduli. So this is, so maybe before I proceed here, let me say just one word on what we know. We know very little here as it stands. And then I come back to the previous schedule. So we know very little here. We know he managed to prove it. So first, if we assume that X is a curve, so it has dimension 1, then there are no rigid systems. And in fact, for rank 1, I was telling you the truth here. And for higher rank, it is true as well. So there are no rigid systems, so rigid objects. But if we relax the curve, you remember our assumption was projective curve. If we relax the projectivity assumption, so if we just assume that X is an affine curve, and then we have to put some condition at infinity for the rigidity assumption, which I don't do now because I will not talk more on this. Then for affine curves, it is a whole work of Katz. It's a huge book of many hundred pages, who studied the rigid systems, and he showed first that the curve here, to have rigid system, we need that X is an open in P1. As we make the genus higher, there are no longer any rigid system. And then he classified really the rigid connections and noticed that they are all coming from hypergeometric differential equation. So I didn't introduce hypergeometric differential equations, but at any rate, it's a subcategory of the Gauss-Manin connection which we introduced. So in particular, it answers positively Simpson's conjecture, but history went the other way. I mean, Katz proved this in the 80s, at the end of the 80s, and Carlos Simpson conjecture came in the 90s. So this is a very important work. It's very, there are really a lot of mathematics. In particular here, there is the appearance of Shimura varieties. So this is one evidence for the conjecture. And the second evidence for the conjecture now touches higher dimensional varieties. And this is due to Simpson and Corlett. This is a very beautiful theorem of Corlett and Simpson. And they proved it for SL2 connections. Meaning i.e. the connection in Abla has rank 2, and then the determinant of Inabla, which is a rank 1 connection, is trivial. And here, in particular, so they show it's true, and they manage with lots of geometry and classification, and at the end, they prove remarkably that the rigid SL2 connections are coming again, so they are coming from automorphic bundles on Shimura varieties. No, not now. I can't do that. You just Google Colette Simpson, they have only one John article. So the third evidence now, and this is all. So the story stops here, but we can make a following remark, and then I come back to the P curvature. We can, sure.
Even in your first case, the reduction here, if you apply Katz's algorithm, you just construct some local systems, and you could try to apply that in some category of trees.
You should speak louder.
Sorry, I mean,
I could.
a satisfactory answer to question one. You can construct these local systems. They're kind of geometric, but can you really verify that they're geometric?
Yeah. You can really out of cats you can construct the projective morphism I was talking about. Yeah, it's possible. Okay. So the answer is yes, but I'm certainly not going to do it. But the answer is yes. Okay. And so the story stops here, the evidence stops here, except that we can make the following remark, is that if Simpson's conjecture is correct, then something else is correct. Then, if we look at the underlying representation of the fundamental group of rigid connection, so if rho from pi1 topological from X, C, base somewhere to G, L, R, C is rigid, then one conclusion, so the fact that it is rigid implies that it doesn't deform to a higher order. So that implies already, without any thinking, this implies already that in fact this representation factors through GLRK, where capital K is a number field. But the conjecture here, if true, implies something more, then it implies that this representation here will stabilize the lattice, a rank R lattice, defined over this number field. Said differently, there is a finite extension, then there is a finite extension, there is LK finite field extension, such that the representation here has image the monodromy group, the rho of pi1 topological, lies in GLR of the ring of integers. And why this? Is because there is one thing I hadn't said, so let me explain this as when you look at this morphism which is here, so maybe I keep it here, the Gaussman in here is written like this, and what is the underlying representation of the fundamental group here? This is the local system associated to it. So this is precisely the local system which comes from, now we should say, the analytic map associated to F, and here we write Z, and then tensor C. So that's the local system. This is a variation of the Betti cohomology of the fiber. So variation of Betti cohomology of fibers. So it has an integral structure, and this is the reason for this. So this is called the integrality conjecture. So let me write this. So, Simpson's conjecture. So let's say Simpson's geometricity conjecture contains as a subconjecture, contains the following integrality conjecture. A rigid representation pi1 topologique to GLRC has values. This is modulo conjugacy here. Huh? This is modulo conjugacy. Has values in GLR of the ring of integer of a number field. So this is a really very arithmetic conjecture, and under this assumption, pardon me? Too late, sorry, I apologize. So then the third evidence, well, it's not really an evidence, but if we assume this, so now I come to 3 here. So if inner blanc is rigid and we assume it is integral, in this sense that the underlying monodromy representation is integral here, and so it's irreducible, and in addition it is now an SL3 connection. Then the conclusion, and this is a recent work of Langer and Simpson, then the conclusion is that it is geometric. So this is the evidence here. And now notice, let me write. So note, intersection of yesterday's lecture with today's lecture lies in the word geometric. Yesterday we had geometric connections, in particular finite connections. We were mentioning Grothendieck's p-curvature conjecture, not yet properly formulated. Today we have moduli, rigid objects. Rigid objects should yield geometric, should be geometric. Okay, that's the intersection. And now I link the two. So I should say here the work of Katz. And here I should maybe write that 1 plus 2 plus 3. This is really complex geometry. That means the work of Katz and the work of Corlett-Simpson and the work of Langer-Simpson, the result has been proved by purely geometric, in fact, complex geometric methods, so geometric methods. At any rate, no one was ever going to characteristic P here. Okay, so now let me link the two things. And to start with, let me reformulate properly. Let me define not the peak curvature. Peak curvature is a bit technical to define, so I'm not going to define it, but I'm going to give you an equivalent formulation. Sure.
For a particular x, like C1 minus the number of points.
Yes.
And I try to construct this family explicitly.
Yes.
But what do I do for any given? How do I deal with any variety?
We don't know. This is a mystery here of the conjecture. This is.
You said that it is true for M2, for M3.
They managed to construct it. Because we know. So to answer your question, so here is the question. He's asking me, how do you construct the y to x to u in x? So in 1, 2, 3, where does y to u in x come from? Okay? Now, for 1, I will not answer, but for 2 and 3, this is either SL2 or SL3. Now, the theory of Simpson is telling us that a rigid object, in particular, underlies a complex variation of its structure. I haven't given the definition. But so if we are in rank 2, a complex variation of its structure, modulo Tate shift, as we say, is necessarily of type 1, 0 and 0, 1. So you expect that it's coming from an abelian variety, and then you do it like this. That means you are looking at the variation of complex Rod structure, and then you show that it is integral, and then you have an abelian scheme, and this is the answer. So roughly speaking. Except that in addition, they show that it's coming from a Shimura variety. And here, so you have 2, 0, 1, 1, and 0, 2. And then they manage to show that essentially this part doesn't play a role, and then they come back to this case, so to speak. Of course, it's much harder than what I said, but roughly speaking, this is the answer to your question. They are coming from Shimura varieties. Thank you very much to ask me. Thank you very much. They are coming from Shimura varieties. Shimura variety, which carries an abelian scheme, so they are coming from ultimately from wet 1 wet structures. So I don't want to enter this. Okay? So this is okay. So now let me reformulate. Let me give you an equivalent definition, not of the peak curvature as an object, but to what it means to have peak curvature 0 and what it means to have peak curvature nilpotent for a connection. So let us start with X smooth. And this X later on will be in fact the mod P reduction of a smooth variety in characteristic 0. So we are here over a field K, and now this K has characteristic P. In fact, it will be a finite field in the application, so in particular, it will be a perfect field. And then, associated to X, we define the Frobenius twist. As follows, we consider X over, so this is a very classical construction, over spec K. Now, on spec K, there's a Frobenius of the characteristic P field, which sends lambda to the power P. And then we do the Cartesian square here. And this is a Frobenius twist. And now, this Frobenius twist is dominated by X over spec K. And the morphism, which is here, is called the relative Frobenius. And let me show you all those maps at the level of algebras, K-algebras. So at the level of K-algebra, I have K here. So now the Frobenius here sends, as already mentioned, lambda to the power P. Now here X is going to be a K-algebra, so let me just write Kx here for to shorten the notation. So it's locally, so X is affine here. And then K of X prime here. This is just sending here what is here, so it's a fiber product. And so that means K of X prime is K of X, so this means K of X prime is K of X twisted over the Frobenius by K here. And then here I claim that we still have K of X by sending now the coordinates here, by sending them to X to the power P in such a way that the composite homomorphism here sends any polynomial here to its P power. Because to send a polynomial to the P power, so when you have, for example, let me write like this. Then the first morphism sends it to some lambda I to the power P xi, and the second morphism here sends it to some lambda I to the power P xi to the power P. And that's the whole P's power morphism in characteristic P. So among the connections, we have those which are coming from X prime. So let us take any coherent sheaf on X prime. So let V prime be a coherent sheaf on X prime. And now consider the following formation. Let us define E, or maybe E prime. Define E to be the coherent pullback of E prime. So what is a coherent pullback? If we just look in terms of modules, so we have here K of X prime. So we have some module, M prime. And now we have K of X. So the corresponding module here, M, this is just M prime, tensor over K of X prime, oops, by K of X. So I don't do any miracle here, but I claim that this is endowed with a so-called canonical connection, which is flat. Let me write nabla canonical, and in on modules here, the connection is just given, so nabla canonical of a section M prime here, tensor a function F. This is just M prime tensor dF. And why is that well defined here? Is because when we ask, so it's well defined, so maybe let me write here, it's well defined as when we take, we multiply, so we have to show that this thing is the same as nabla canonical of M prime tensor lambda F via the action. So let me write a point here, but the action here is just raising the coordinates to the power P. So this is Frobenius pullback here, but raising the coordinates to the power P kills the differential. And that gives precisely this. So that means this is well defined. And this is called the canonical connection, so well defined as D of lambda P F is lambda P dF. okay? Okay, so that's a canonical connection, and now we pose the definition. So notice here, I said that to a few among you yesterday after the lecture. This shows here that in characteristic P, the category of connections, flat connections, is not Tannakian, because this E prime here can be taken to be any coherent sheaf. In particular, it's not locally free, not necessarily locally free. So E prime, not necessarily locally free, which implies that in characteristic P, category of connection, of integrable connection, is not Tannakian. So anyhow, so now we say, we come to our definition. So here it was the preliminaries before giving the definition. We have inabla. And I forgot to say that a canonical connection like this is obviously integral, so it's flat, because when you do it twice, you just do D twice, and D is flat. So an integral connection, integrable connection, we say has a P curvature 0, if and only if, so if and only if, it is a connection of this type. So there is an E prime on X prime such that inabla is just Frobenius pullback of E prime endowed with a canonical connection. So we say here, as I said, usually one defines the P curvature in all generality, and then one computes what it means to have P curvature 0, and this theorem is called Cartier descent, and we should say Frobenius descent. So at any rate, this is a condition. And likewise, we can say or not likewise, but more generally, we can say what it means for a connection to have nilpotent P curvature. So inabla has nilpotent P curvature if it is filtered as a connection, filtered, such that the associated graded connection has P curvature 0. Okay, so now let us see together that if we start with a finite connection in characteristic 0, so see together, this we can do together. If we start with a connection in characteristic 0, so let us write proposition. Let inabla be a flat connection on X over K of characteristic 0. Now, a flat connection is a datum of algebraic geometries given by finitely many conditions. The variety is defined by finitely many equations because it's a variety, it's a scheme of finite type. So that means this whole situation here has a model over a scheme of finite time over spec Z. So there is X, S, E, S, nabla S. So S, scheme of finite type. Over Z. Such that together with a complex point, such that our X, so such that our X in nabla comes via base change from a situation which is spread out arithmetically. So then we say that if we assume that the flat connection has finite monodromy, then if the flat connection has finite monodromy, its P curvature, so that means its P curvature means the P curvatures of its mod P reduction, I explain immediately, but let me finish the sentence, are vanishing, are zero. And now this word here, the mod P reduction, we have a relative situation here, so that means our connection here goes from ES to omega 1 XS over S tensor over OX over S with E over S. And then we can take close points. So close point has finite residue field. So let's say nabla S here. And then we can reduce, we can specialize at the close point. So we look at nabla little s. We restrict the connection here because the connection is relative, it's linear in the horizontal direction. Anyways, S is a finite over the base, so there is a finite over spec Z, finite type over spec Z. So, so we, if for example S was really an open in a number ring, then if looking at the relative differential forms or looking at the absolute differential forms would be the same on an open of the number ring where it is unramified over Z. But in general, S might have several transcendental variables. So we look at relative differential forms here. And then we have here, so relative to S is a close point, so the residue field is finite, so there are no differentials in the field, so whether I write S or not, it doesn't matter here. And then the mod P reduction are precisely the reduction here at close points of the scheme, so this is a mod P reduction. So one should say the mod S reduction, the mod P reduction, but this is a classical terminology. Mod P reduction means the restriction at S. And when we say the P curvatures mean mod P reduction are zero, and then usually you have here for almost all P, and here it means, for this expression for almost all P, it means precisely, one just has to think a little bit, it means that it has to be true here, the P curvature is zero for all close points of a non-empty open of S. So IE. So let me write here psi. Let me denote the P curvature here. I call it psi is 0 for all S in, let's say, S prime in S. This is open and non-trivial. And this open here is constructed by looking at why. Let me explain. Because we saw yesterday that finite monodromy means that there is a y over x which is finite, étal, let's say h, such that the plural connection here is trivial. So this was the last characterization. We came at the end of the day to a characterization which is purely in the framework of algebraic geometry, no transcendental explanation here. And so this cover here is in fact defined over some open, let me call it some S, maybe not the same, maybe not the optimal S we had before, but this is defined here. So when we restrict here to a close point, such that we take S so small that when we restrict to close points, this is still finite étal. Then our restricted connection here trivializes here. But then, because it's trivializes here, when you look at the Frobenius here, and then you look again at, so let's say prime, this induces a prime here, and then you show that this is a fiber square. So here, this is because HS is étal. This implies that this is a fiber square. And well, here, this is a relative Frobenius. And consequently, this factor here, this to say that it trivializes here, it says that the connection here is recognized in as a subquotient of the pullback connection as we explained yesterday, and then the solution, this E prime, is precisely coming from a subquotient here of this push down of the structure sheaf. So E prime arises as a subquotient in H prime lower star of O Y prime S. Okay, so that explains, this is relatively easy to understand. And now you have a proposition of the linear. So this is for finite connections. And now we have a proposition of the linear, which is, this is, unlike many of his theorems, this one is not so hard to understand. So let us write proposition. That if E nabla, so if K has characteristic 0, well, in fact, it doesn't really matter. So let me write, yeah, it doesn't matter. It's more general than this, but let me write like this. If K has characteristic 0 and E nabla is a Gauss-Manin connection, then when we make a spread out as explained here, that means we look at a scheme of finite term over spec Z over which everything is defined. So it's a Gauss-Manin connection, so it's coming from a Y to X, F, which is projective smooth. And then it's a relative variation of the relative Durham cohomology. Then when we make a spread out as before, then the link is telling us, so we look at XS and ES nabla S, which in fact is coming from a spread out of the whole situation here. Then we look at the reduction, so we look at close points. And we look at the reduction here. Not the reduction, the restriction. Then in fact, those have nilpotent P curvature. So So now the optimistic generalization of the Grothendieck-Katz conjecture of the Grothendieck-Katz P curvature conjecture stipulates or predicts that if in Abla in characteristic 0 has nilpotent P curvature, nilpotent P curvatures, as before for almost all P's, that means for all S of a non-empty open of scheme of definition. Then we should have the conclusion that in Abla is of geometric origin. Because I forgot to say one thing here, the proposition of Helene is that Gauss-Manin connections have nilpotent P curvatures, of course, extends to subquotients. So if it is a Gauss-Manin connection, it has P nilpotent curvature, and likewise for subquotients. Because by definition, here this implies likewise for any subquotient, because it's a subquotient of this connection. If this one has nilpotent P curvatures, and the P curvatures of the subquotients are just the P curvature is just one block of the matrix of the P curvature here. So clearly, this is really. We don't know when this will be understood. But now, coming back to what we said before, so this is really a big dream. But what is not a big dream, it's a concrete theorem, is that this direction, that if we have something of geometric origin, it has P curvature 0. And Simpson's conjecture predicts that rigid connections are of geometric origin. So in particular, they should have nilpotent P curvature, in particular. So now I propose the program in the fall saying, so remember, so now we have like 25 minutes. Now summarize the situation. The discussion we have seen that on one hand we have Grothendieck-Katz conjecture, and so conjecture. But in fact, of course, the conjecture is vice versa. If the P curvatures are 0, the connection should be finite. And but the one direction, we did it together. If we have a finite connection, then we have P curvature 0. That we basically computed together. So we have but still I write conjecture. I will use only in the philosophy here the easy direction. So let me write here, it's coming from finite in characteristic 0 implies a P curvature 0. Okay? So the hard thing is the other direction. And we have the generalization of this. We have the line, which now we say geometric in characteristic 0 implies P curvature nilpotent. Okay? And we have Simpson, which says rigid implies geometric. So in particular, so we had seen that this implies that rigid implies integral. At the level of representation of the topological fundamental group, we have already argued that if Simpson is correct, then we have the integrality conjecture. So on this side here, we are purely on the topological side. And in fact, which was called yesterday the analytic side. And when you remember the Kronecker theorem I was telling you about A and B, so we are on the A side here. Because we are looking at the monodromy group and we want the monodromy group to be arithmetic in some sense. We don't say that the monodromy group is arithmetic, this is not what I mean, but at least it is integral in the sense we said. And yesterday, you remember this integrality was precisely, A was an algebraic integer. So this is precisely this. Now, finiteness was coming that, from the fact that the module was 1, and this is not contained here. And now I propose to say, well, we can also go mod P. That means we go to the B side of Kronecker's theorem, and then we try to see whether the P curvatures fit with the conjecture. So we say, second corollary of Simpson's conjecture, oops. So conjecture of Simpson, so geometric conjecture of Simpson implies the following conjecture, so this is still his conjecture, so to speak, it's a corollary of his conjecture, is that if X is smooth projective over K of characteristic 0, and if I nabla is rigid, so it's always irreducible for us. If it is rigid, then its P curvature should be nilpotent. It should be, and then of course, in the most ideal world, that would be it. Because the big conjecture is telling us that if a connection has nilpotent P curvature, it should be of geometric origin. But clearly we are zillions of years away from understanding this. But this is a concrete question. And what is behind the program here? So I should say here is that in fact it is now a theorem since a few weeks, together with Groschenik. This is yes. But in fact, more is true. Because this program here, it's not only by analogy here. Let me explain the program which is behind. It's because, and that I can say more in the last lecture on Friday, it's because another way of phrasing P curvature nilpotent, let me say this. So another way of phrasing the property that the P curvature of nabla little s, so E little s, nabla little s is nilpotent, is to say, and now comes a beautiful p-adic geometry. So far, notice that we were talking on characteristic zero geometry, and we were going to mod P geometry, to geometry over finite field. And now we do something intermediate. We go to p-adic variety, so it's in the middle. So is to say the following, remember that we have excess. Here, S was a finite type over Z. And now we take, so we were taking a closed point, and now we take a closed point, and we take a W lift of a closed point. So we are looking, so let us denote by K little s a finite field, which is a residue field of S. And for example, assume for simplicity S was an open in a number ring, for simplicity. Then I take a S which is not ramified. So then I have the localization of the number ring at this point, localization and completion, which is the same as the ring of int vectors with values in this, in this residue field here. So I take, and in general, if S is not an open in a number ring, then I take a WKS point. I mean, I can assume that S is unramified here because, as I said, everything is formulated by the existence of some non-empty open. So then we look at, so that means we complete here. So we look at here. So I just abbreviate by W here. And now, so we have our connection here, so that means we have completed at the point we are looking at. So let me denote by W here for simplicity of notations. And then we have, now we denote by capital K. Pay attention, this capital K is not the one which was in the monodromy before. That's the field of fractions of W. So this is a p-adic field. In fact, it's an unramified p-adic field. And we look at the corresponding p-adic variety. So I apologize for the drawing here. So I should write spec each time. I'm a little bit lazy here. Okay, so this is a fiber square here. I made a mistake, pardon me?
Special fiber.
Special fiber, no, this one special fiber? Ah, yeah, that would be the little s, but this one is a capital S. But you are completely right, so this is very good. So let me write what you said, thank you very much. Let me write a spec of a little s here and x little s here. I apologize, it's hard to distinguish. So that's the fiber over the finite field, and this is a p-adic lift here, which is God-given here in our geometric situation, okay? So now what does that mean? Now I come to my discussion, because this is, of course, you will see what comes. It's a fantastic thing, is that to say that the p-adic connection, that means a connection restrict to x capital K, so to say, I'm sorry, that the P curvature is nilpotent on the mod P scheme here is equivalent to saying that the connection on the p-adic scheme here is an isocrystal. So here, I continue my sentence here, is equivalent to saying that E, let me write capital K here, nabla capital K is an isocrystal. Okay, so I just throw the word like this, but now this enables me to go further, because an isocrystal, we know that when an isocrystal comes from geometry, not only it's an isocrystal, but in fact it has a so-called Frobenius structure. So I cannot explain right now what is an isocrystal. We still have one session on Friday I can explain. But if Simpson's conjecture is true, then not only conjecturally that should be equivalent to saying the P curvature are nilpotent, but as I said, this is far beyond our knowledge right now to understand this equivalence, but we are able to prove that the peak curvature is nilpotent. So the next question would be to go from the other side, purely characteristic P, we leave to p-adic field, we forget the monodromy representation, so to speak, the purely topological invariant, and we say, if this is really geometric here, then it has to be the case that this isocrystal has a Frobenius structure. And that's the second theorem. So still, all now what I say is with Michael Groschenik, who is a fantastic young mathematician, who is currently in Berlin on a Marie Curie fellowship. And then this isocrystal has a Frobenius structure. So this was really the program I proposed with an isocrystal has a Frobenius structure. So let me write here. And now to give you the test for the last lecture, let me tell you more, because if it is an isocrystal with a Frobenius structure, and if we were on a curve, we are not for this problem, because I explained at the beginning that a smooth projective curve does not have any rigid connections. But if we were on a curve, now we would have on a curve, so if, let's say abstractly, if X is a curve, and now this is this little s, it's a curve over a finite field. Then we know, thanks to the work of Laurent Laforgue, and the translation from the L-adic word to F over convergent isocrystals. Here there is no over convergency condition because X is proper. So the work of Tomoyuki Abe. We know that in fact, those Frobenius isocrystals, they are in the sense of isocrystals, they are of geometric origin. So we know. So this is a consequence of, so this is Laurent Laforgue, that those Frobenius, I just write F here, isocrystals are of geometric origin. But as an isocrystal, which is a much weaker condition, that's the one Carlos Simpson is requesting here. So this gives the inspiration that, this is a good thing. And in fact, but that of course, we cannot translate to characteristic zero. So we cannot use, or at least so far, so let's say so far, in our problems here, because of two reasons. The first one is obvious, is that X is a curve. The theory, Laforgue is a Langlands program, Langlands duality. This is always for global field, and there is no higher dimensional analog of automorphic form. So if we replace the curve of a finite field by a higher dimensional variety of a finite field, there is no, so far there is no theory of automorphic form which would enable to carry over the program. So this is a curve, so we are stuck. And the second thing is that it is in the sense of isocrystals. So, one second. And so one should be able to live to characteristic zero, and we don't know that. So this condition is related to the existence of certain vanishing cycles functor, which we are not able so far to, or let's say AB is not yet able to construct. Nonetheless, I will answer later your question. Nonetheless, we still have 8 minutes, so I can say more. It's because now I go to the program, not the theorem of Laforgue here, but the theorem of Laforgue was in particular answering in the curve case, a conjecture posed by Helene in Vel 2 on the existence of L-adic companions. So I will explain this on Friday, but let me write the keywords here. So Laforgue, so Laurent constructed on curves over finite fields, LAD companions. I will explain this on Friday. We are short of time here. Which is a positive answer for curves to Deline's conjecture in Veil 2. Deline was also predicting crystalline analog of his precise conjecture. It's a very precise conjecture. I have no time to write it down, and I won't on Friday, but I will explain a little bit around. What did I want to say? Yeah, he had no time to. He said there must be a crystalline there must be a crystalline side to the story, and this even the formulation has been made precise by Crew later on, and the work of Laforgue combined with the work of Tomoyuki Abe shows, in fact, that there is a perfect companion theory to L-adic shifts on one side and F over convergent, and so I just write here isocrystals on the other side. But this is on curves. Now, I finish the lecture today by saying this. So this was 2013, just before relying on work of Deline on the existence of a certain number field which captures all the coefficients of the local characteristic polynomials of the Frobenius at close point on a given L-adic sheaf, then Drinfeld proved 2012 or something, he proved that if X is smooth, then let me just write L-adic companions exist in a higher dimension, in any dimension over a finite field, then L-adic companions exist. And with Tomoyuki Abe, we could not prove that we have a correspondence L-adic companions and over-convergent isocrystal, but we could prove that to F over-convergent isocrystals have L-adic companions. So this will have the following consequence for us. So the companions have in particular the property that when we say companions here, it is equivalent to saying that the L functions, let me just write here, are the same, but I will explain on Friday. I will explain what it means. And here this is the same thing. The L functions are the same, capital L. And this enables one to show here, using those companions, so using this, and using this and Falting's p-adic Simpson correspondence, Well, in fact, Falting-Simpson correspondence we don't really need for this, so let me just write, I will say more on Friday. Using this, one can show a weakening of the integrality conjecture of Simpson, so integrality is that it's true if in addition the point of the moduli, you remember integrality conjecture was saying that a rigid connection has integral monodromy in the sense we said. And here we have to reinforce a tiny little bit the notion of integrality, of rigidity, I apologize. Rigid was an isolated point of the moduli. And now we request the point to be not only isolated, but to be smooth. So true if, in addition, to be isolated, the moduli point is smooth. The point here is that it's a cohomological notation. It's a cohomological. It's a cohomological condition. And this cohomological condition is seen by the L function. If you like, to make it a little bit polemic, this would be like taking Nick's second part of his lecture and saying the derived stuff here we don't need. Okay, but I stop here and I will explain what is behind here. And I will explain a little bit of the method to prove Frobenius structure not, because this is more arithmetic, but I will explain a little bit of the proof to show that the P curvatures are nilpotent, because this is geometry, this is characteristic P geometry, which is very nice and which relies partly on the work of August Vologodsky, and I was told that Vologodsky is coming back to Moscow, so I think it's the right thing to lecture on. And I thank you for your attention.